I am William Chen, Developer Relations at Terra, and today I'm going to be covering smart contracts on Terra and why you might want to consider building your next app on Terra's DeFi infrastructure. So, Terra is a decentralized stablecoin with global ambition, backed by its sister token Luna, which is the native staked asset of the Terra blockchain. Luna collateralizes the entire Terra economy and provides governance voting rights to its holders. Luna effectively represents a long-term investment in the Terra economy by trading the instability of day-to-day price fluctuations and providing stability to the Terra ecosystem. Luna holders receive a consistent stream of TX fees that only go bigger and stabilize the incentive to hold Luna. So the main topic is why build on Terra. So Terra's smart contract feature is new and nascent and definitely not mature, but I'm gonna just go over a couple reasons why you might consider Terra as a potential candidate for your next smart contract. So first of all, I'll have to go into the consensus and block finality of Terra. So Terra is a delegated proof of stake consensus chain based on Tendermint BFT as a Cosmos SDK chain. How it works is that the top 100 validators in Luna Stake participate in the block production process. And we're lucky to have a proactive validator community who's actively developing tools such as block explorers and validator notifiers and other tools. Currently, we're at 6 sections per block with finality, and we have support for potentially hundreds of transactions a second. Terra is a chain that is ready for DeFi applications. So, our stablecoin mechanism was built with world e-commerce in mind. So we currently have the Korean won, the US dollar, the Mongolian Turkic, and it's just a marginal cost to add an additional currency to the Terra ecosystem. We have a robust price oracle system that reports on the price of Luna every 30 seconds, and we have fast native on-chain swaps between currencies, between Luna and Terra, and between Terra and Terra currencies. So Terra is really implementing something called money as a protocol, whereby we're creating money that has its own algorithmic and monetary fiscal policy. So this, coupled with the governance feature, enables Terra's economy to act as a sovereign economy driven by its users. The main appeal of Terra, however, comes from the growing, highly active user base with real-world usage. So currently, Luna is third in transaction fees, right after Bitcoin and Ethereum. There are a total of 1.6 million total accounts after 1 year of release, and this number is constantly growing. And we're integrating with real-world apps with actual use cases. So some that come to mind are definitely Chai and Mimi Chat, which are payment processors that provide discounts to attract users. And Chai in particular is responsible for much of Terra's growth as growing out from Terra. And what's cool about Chai is that it's gotten so big that you can use it at convenience stores, buy groceries with it, integrated in places like We Make Price and Timon, and currently partnered with some of the largest e-commerce retailers in Korea, including Nexon and Kyobo Books. Another interesting use case that Terra has been implicated in is with high yield savings products. So Terra provides this stability feature where for Harubank and Trinito, you can deposit KRT and earn high interest on that KRT compared to a traditional savings account with a bank. So right now, I'm going to spend the rest of the presentation talking about how you can use Terra with the SDKs and how you can start programming things with Terra and eventually use smart contracts. So there are currently 2 Terra SDKs released. One is called Jigu. It's for Python 3. And the the other one is called Terra.js, which is for JavaScript. In this workshop, I'll be using the examples with Jigu, but the concepts will be easily translatable into Terra.js with a bit of looking at the documentation. So how Jigu works is that it's a library that that enables you to talk with an LCD node. An LCD node is something that a TerraD node runs that exposes its functionality through an HTTP interface. So instead of having to make raw HTTP calls and do serialization and deserialization of the requests and responses, Jigu will handle that all for you and enable you to work within Python as if without realizing that you're working with strings and raw blockchain data. So it allows you to create Pythonic code that works with the Terra blockchain. So once Jigu parses your requests, your request is sent to the LCD and propagated through the rest of the network, and this is how your Python application can interact with the Terra blockchain. So you can get testnet tokens at faucet.terra.money, and this may be useful if you're wanting to follow along with this tutorial. So Jigu does one of 2 things, and the first thing is querying data. So the blockchain exists out there, and you want to get information about the blockchain into your program. The first thing you want to do is create a Terra object that connects to the LCD. And once you've created that, okay, so here I'm connecting to Soju 14. Soju 14 is the official testnet as of time of recording of the Columbus 3 mainnet, and I'm using the public LCD node at https lcd.terra.dev. And you'll notice that each of the functions are neatly packed into its own submodule within the Soju variable. So I can get the blocks by doing soju.blocks, and there's even an iterator which allows me to iterate through the blocks. I can get the balance for an account by using the bank module. I can get the exchange rate for Luna in USD using the Oracle module. And I can get the market parameters and print them using the market module. So it's really short, and it's really easy to get data from the blockchain by using the functions within each submodule. So the second thing that the Terra SDK is able to do is to affect change on the blockchain by creating transactions and broadcasting them. So like before, you're going to connect to an LCD. Here we're going to make a wallet, and a wallet just is an abstraction around a signing key. Here I'm using a random mnemonic key, which gives the wallet signing features. So I'm going to create a message, and a message basically contains all the things I need to interact with the module to change its state. Here I'm using a message send, which is the most basic way of telling the blockchain to move my balance into someone else's balance. So I'm specifying a balance of 23 Luna. Here the unit is ULuna, which is micro units, or 10 to the negative 6. So 23 million microluna is 23 Luna. I'm going to specify a fee, and I'm going to send the message. I'm going to sign the message and create a transaction. And then finally I'm going to broadcast that message. then you should see a successful transaction, and then you can go into Terra Finder, look up the transaction hash, and you can see the exact transaction being posted from Python. So I just wanted to point to the fact that you can actually put multiple messages in a TX. So you can, okay, here I'm doing two swaps, one from Luna to USD and the another from Luna to KRW. And first I'm going to specify a fee that's higher than the one before, because this is going to require more data. And then I'm going to sign the messages and create a transaction and broadcast like before. So this is how you can put multiple messages inside a transaction and broadcast it at the same time. So you can think of messages as transactions in Ethereum, because messages kind of are the ones that are actually performing the state changes. So now if you've gotten a bit more comfortable with the SDKs, just exploring around the documentation in exploring each of the different modules and each of their functions, as well as creating different types of transactions such as message delegate, message undelegate, and playing with other things other than message send and message swap. We can progress to the smart contract section. So smart contracts are powered by CosmWasm, which is led by the Confio team, and I'm going to include a video after this where they explain more about the system they've created. But what they've been able to do is create a system where you can execute WASM smart contracts or WebAssembly smart contracts on the Terra blockchain. So what makes WASM or WebAssembly an ideal execution environment for smart contracts is that it is designed to be a portable compilation target with small binaries, small dependencies, and works at a sufficiently low level to be and is designed to be portable and safe, which are all the things that we want in a smart contract execution environment. The other thing is that the way that CosmWasm has designed smart contracts is that they have potential to be multi-chain smart contracts. So in one sense of multi-chain, you can almost like write one contract and then deploy on multiple chains. And in another sense, once IBC rolls out, contracts will be able to call other contracts on other chains through IBC. So currently, we only support Rust for writing smart contracts, but the CosmWasm team has expressed the possibility of porting the libraries that they've created to other things such as AssemblyScript and TinyGo. So the scope of possible languages to cover CosmWasm smart contracts is potentially much larger. But right now, the only sort of language runtime for which mature tooling exists is Rust. So unfortunately, we'll have to use that. But I don't think that it will hinder too many people from using CosmWasm, because the amount of Rust you need to know is actually quite minimal. You just need to be familiar with the simple borrowing, and because smart contract logic isn't supposed to be too complicated. If you can implement your contract with a bunch of read and writes and managing balances, doing a bit of arithmetic, you should be good. So I'm just going to go over the smart contract architecture, or what you need to write in order to write a smart contract. So a smart contract revolves around 3 entry points. defined as functions in your Rust code. So the first is the constructor, which sets the initial state of your smart contract, and this is sent in a message instantiate contract. The second one is a handle method, which will implement the different functions of your contract. So, for instance, if I had an ERC20 token, the handle method should be able to receive different requests on, or different functions through the handle message, and implement things like burn, transfer, approve, etc. And finally, you have to define a querier, which tells the contract how to get data and interpret it back into a form that users can understand. So this is just the workflow of how a contract writer creates a contract on the Terra blockchain. So a contract writer will write his program first in Rust, and then compile it into a WASM binary that he will include in a message store code. Once he has this message store code, he will send it to the blockchain, and the WASM module will sort of store the code on the blockchain. So here, CosmWasm has decided to learn from Ethereum and realize that that they should decouple the storing of a blockchain of a smart contract's code and and the actual instantiation of a contract. For example, there can be many contracts that use the same code, such as one ERC20 token code being used by multiple ERC20 implementations. So here we see the same code being used in two different contracts by contract creator A and contract creator B, each with their own init message, which customizes the contract. And then the module assigns a different contract address to each contract that has been created, as well as the contract's own private state. So here's an example of how you can use Jigu to upload code to the Terra blockchain using these messages. So as before, what we want to do is create a message, put it in a transaction, sign the transaction, and then broadcast it. It's a very simple process, so I'm just going to walk through. First, you're going to load the contract file and then encode it into base64. Next, you'll create the message like before, and then you'll broadcast the transaction. And at the end, you'll get the code ID, which is in the blockchain events, and that is just the code ID of the code that you uploaded, but no contract has yet been created. Next, we'll go over how to instantiate a contract. So remember that we had saved the code ID from the uploading the contract before. Now we want to instantiate a contract, and then we're getting a contract address back. So here I am creating the message using the code ID I had that was returned to me from the last execution. And you'll realize that the init message that your contract understands is actually a message in JSON that gets automatically parsed by your contract into the right configuration. Here I've decided to name my token William Coin with the symbol WILL, and you can see that you can also put an initial amount of coins to fund the contract. So I'll just broadcast the transaction and get the contract address, and this should create my contract. So now my contract will exist at a normal Terra address. So this is just simplified flow of how a contract gets executed. So the contract user will define the function that he wants to call on the contract, such as transfer or burn, and put that in a message called a message execute contract. And then he'll sign and broadcast the message execute contract, which will get handled by the WASM module, and load the contract code with the handle message, specifying the arguments to pass to the contract's handle function. Next, the contract will be able to access the state and commit more state. And finally, when the contract when the contract finishes execution, the contract can affect the rest of the blockchain by producing by emitting its own messages like message swap, message send, and message delegate. So here's an example of executing a contract. So we'll create a message and we'll use the contract address that we got. And you'll notice that the message or the handle message is JSON. So here we're trying to use the transfer method of the contract with 5,000 as the amount and a random account as the recipient. And there is also an ability to add coins to the contract with your contract call, which will be required for some contracts, such as like a vending machine type contract where you have to deposit some Luna to effect an execution. And the contract can actually pull which types of coins have been sent to it and see if the fee paid is enough. So we'll just broadcast the transaction and that should execute the contract. So it's that simple. So finally, how do we get data actually out of the contract? So since for my last example, I transferred some coins from one account to another, the one thing I want to be interested in is perhaps the balance. So I need to create something called the query message that the query function on the contract will understand. So the query message is JSON, like the init message and handle message. And there's no transaction needed. Just query the WASM module. And the output is JSON. So as you can see, the Terra integration for smart contracts is very simple and just adds 3 messages and a querying mechanism to the Terra blockchain. But this allows users to commit arbitrary code to the blockchain and finally allows third-party developers to add their own logic rather than depend on Terra's native modules. So I'm just going to talk about the developer tools that we're working on that we'll be seeing in the next couple months. So the first is Local Terra. Local Terra is a one-click blockchain and ecosystem tool for Terra. So what it does is it spins up an LCD node, which is a Terra node REST API server. It spins up FCD, which is a block indexer, which is the backbone for Station, which is a wallet, and Finder, which is a blockchain explorer. And it gives you a way to quickly control and inspect the world state, which makes it easy to speed up smart contract development and testing. Next, we're going to create an easy way to set up the general boilerplate for writing a DApp front end. So we want to make it as easy as creating a new React app with yarn create Terra DApp, and this is going to allow people to quickly get set up with a usable front end to use with their smart contract. This will lower the barrier to entry by getting you set up quickly with Terra blockchain. And finally, we're planning to release a Chrome extension version of Station, which will bring the MetaMask or MyEther wallet experience to Terra and allow you to allow users to directly interact with smart contracts from within a website. So that mainly covers how you can get started with smart contracts, and you can get started today with the smart contract documentation on the Terra official documentation available at docs.terra.money. Right now, I'm going to pass it over to Ethan Frey of CosmWasm, and he's going to explain more about the mechanism that allows Terra to run smart contracts. Thank you.
Hello, My name is Ethan Frey, and I'm the co-founder and CEO of CosmWasm. Today I'll explain what CosmWasm is and why it might be interesting to you in your project. First of all, what is CosmWasm? CosmWasm is a multi-chain smart contracting solution. That means we are not a blockchain. Rather, we are a module that can be embedded in many different blockchains and is currently many different blockchains. That is a very powerful point. I will break it down in a few ways. What it means currently is if you are a developer, you can write contracts that run not just on one chain, but on many different chains and leverage the same contract and same knowledge many places. As a blockchain and you want to add smart contracting capabilities, you can embed CosmWasm into your blockchain. And that allows you to access existing contracts in dev community for many different blockchains. So we don't have to lock each one and learn a new language for each blockchain. We can have one that is generally extensible. We also have deep Cosmos SDK integration. Currently, the only platform that we are integrated with is Cosmos SDK. We would like to extend that in the future once we hit more stability, like our 1.0 release. But that allows, there are dozens of different projects currently building on the Cosmos SDK. Most of them have lots of different modules written in native code, Go code, to add custom functionality. And this allows us to have contracts that don't just run side by side, but actually call into those native contracts, this native code, and allow the native code to call into the contracts. So we allow deep integration into the runtime. That can be customized for every different blockchain. We have a security-first design. When designing CosmWasm, we didn't start with what's the easiest way of making something, let's copy Solidity. We said, how do you make a secure platform? Typically, we see Solidity is really easy to get started writing a contract, but pretty hard to write a secure one. And there's a huge rage for bugs in there and audits and a huge community there. And that seemed very dangerous. So we said, we can raise the bar for writing a contract, make it a little harder to write a basic contract, but lower the difficulty of writing a secure contract. And this space here is a space of actually functional but insecure contracts. So we're trying to lose that space and say there's not much space for that. There are some issues which you can document, but we try to limit the number of issues that you can bite you when designing smart contracts. And we are now refining the user experience to make it easier and easier to write contracts on that system. We are based on the WebAssembly virtual machine. We do not write our own virtual machine. We are using WebAssembly. WebAssembly is available in all browsers, but also there are quite a few native runtime solutions that run it. One is Wasmer, but there's WasmTime and CraneLift, and there are quite a few other out there that run as binaries on multi-platform systems. We are using that virtual machine. It's a well-defined virtual machine. There are many implementations that run code from that virtual machine and optimize it, the compilers. And there are many different mature languages that compile down to it. So we don't need to reinvent the wheel. We can choose one of the virtual machine implementations to use, and we can choose various languages that compile down to it. We currently focus on Rust, and we're looking at more. There are probably 6 to 8 languages that compile well to WebAssembly, and another dozen or so that are working on that support. And we're currently live on testnets from 5 projects. So this is not a theoretical idea. This actually does have users. The history of CosmWasm, where did this come from? So first of all, my name is Ethan Frey. I was a third developer at Cosmos, if you've heard of them. They're probably top 20 chain now somewhere. And I got inspired by them with the Tendermint. I started working on Tendermint and then got involved with them. I came in there because I'd been working a lot of back-end web design and wanted to get into blockchain. I was frustrated with the tooling on Ethereum, for example, and Solidity in 2016, and wanted to say, I want to have secure development. I want to have easy development on blockchains, and it was amazing what they were offering with Tendermint. You just worry about the app logic and not all of the rest of the blockchain. And it was written in Go, which is a language I knew and had good tooling. So I built the first Cosmos SDK in 2017. I worked on the IBC white paper then, and I'm really committed to the Cosmos ecosystem. So I've left Cosmos and worked on other projects around them, building on the same technology. And at the Cosmos Hackathon in Berlin, 2019, we had a nice, cool team. So we ended up with Aaron from Regen Network, Jehan from Altea, Shane from True Story, and Pedro from Wallet Connect. And we also had around like 5 leads of projects. We just made a little team. We said, let's build something. And ideas went out there. And one of the ideas that just stuck, we were sitting around there. It was just starting Saturday, and Friday evening, we're sitting around the table drinking and chatting ideas. And it came out, let's build a smart contracting engine. WebAssembly. There's tooling around it now. Everyone's doing this thing. Can we build a WebAssembly smart contracting platform and integrate it into SDK in 2 days? And, well, the later at night it got, the cooler the idea seemed, because, well, it seemed like a stretch goal, but an awesome project. So we tried it, and we basically banged out code for 2 days, very little sleep. I'm very, very thankful to Jehan, who was a Rust expert. I was just learning it while coding, and I brought a lot of the Go code in there. So we were working on the Go side, Rust side, we integrated, learned from each other, and got a working prototype in 2 days. And Pedro threw a UI in it so you could actually view the contracts. So that's pretty amazing stuff to get done in 2 days. So we got it, presented it, people were impressed, and we got a grant to follow up from the Interchain Foundation. And I worked part-time on that alone, basically, from September 2019 to January 2020, and got a 0.6 release, which was basically stable. It was usable, it had gas metering, you had the basic functionality, you could write contracts. It didn't have deep native integration, but you could move tokens around. And it was actually pretty cool, and people started using it. I got docs out there, people started building on this. They're very interested. And since then, we've built out, we got another grant, and we've gotten some contracts and built up partnerships with people that are building on it to get to the 5 different projects building on it actively, and many more interested. So we have a small team now. We have 5 people working on this to bring it to really production ready. And we've added quite a lot of features that people have requested. And we run currently on a few incentivized testnets, and this is getting very, very close to mainnet ready. So we are currently planning a 1.0 release around August. This will be stable, forwards compatible. We provide, if you write contracts on 1.0, we will provide upgrades for the module. We will allow those 1.0 contracts to run on a 2.0 chain, etc. So this is really something that can run a mainnet. We have an audit at this one point, bug bounties on it. And we'll start building out developer tooling around it because you have a stable framework to build on. Currently, we support Rust, and both the runtime and contracts are written in Rust. And we are working currently on prototyping Go via TinyGo and assembly script contracting languages. And they're waiting on the stable APIs. And we have some first experiments on them. We're also working on a front-end framework to build DApps that wraps it called CosmJS, which is similar to Web3 in goals. It's different design, but similar goals. You can quickly add a JavaScript front end that will talk to your CosmWasm contracts. And on that, we can start building better dev UX tools, deploy tools, debug tools, analytics tools, because we have a stable API. And it guarantees that there's a clear path to port it in the future. Your 1.0 code should work on 1.1 and 1.2, and we should have a clear path to port it to 2.0. So this is the point we can really start building a large community of people building lots of tooling around us. So really excited to get more people using it, and it's really going from early adopters to from pioneers and early adopters. So it's usable now, not just on experimentation, but really going to be usable for building production software. And we look forward to building custom solutions, helping people build contracts and integrating with their custom chains. So really, we have the capacity to help people build the solutions they need. So we are looking to onboard more developers and more projects onto the system, principally. So if you want to have CosmWasm on your chain, talk to us. And if you want to learn how to CosmWasm contracts and run your contracts on lots of different chains, great time to learn it. After that, our next stop is IBC support. IBC is inter-blockchain communication. It's Cosmos' flagship design. It was written in the 2016 white paper, way ahead of its time. I worked on refining a very clear technical spec in 2017. Chris Goes has gone in 2019 a very, very much more extensible spec. It's basically TCP/IP of blockchains. It allows this SSL on top, TSL, and everything on there. It allows super secure ways of proving with like clients on both sides. You can send packets between blockchains. It's asynchronous message passing with receipts, guarantee delivery in order, timeouts, all of it on the protocol level guaranteed. And you can start building distributed systems on top of that. So you can make API calls between blockchains. Your contract writes something and you guarantee it will read it or get an error message passed back within certain bounds. So that allows you not to trust an oracle or a special privileged relayer, but really it's really powerful. So you can start building multi-chain solutions that you can have contract in chain A and chain B communicating with each other. So you can have your DAO over this chain controlling, sending money here and controlling your assets in a DEX on another chain. You can move your tokens over here, you can trade them, you can stake them for staking derivatives, you can send them back over here as you want, and that all can be controlled by logic on multiple chains. This is coming out in Cosmos Stargate, should be later this year, and we will have a 2.0 release built on Stargate that supports that. And that will allow us not just the chains and the native code, but smart contracts to send messages to contracts on any other chain. Currently only supports Cosmos SDK. Many other BFT consensus engines with proof of finality can be adapted to support light clients and IBC. That includes Polkadot's Grandpa, Avalanche from Ava Labs, and Nia Protocols. Those all are theoretically compatible with IBC because they provide instant finality, and they can provably say this block is in the chain or not, rather than probabilistic proof of work finality. So this allows a truly multi-chain solution. Once that's implemented, not only will you be able to run the same contract on multiple different chains, but these contracts will be able to run over the chains. So you can have some options contract running on the DEX chain, which actually has native code to run a DEX, really high quality, and you can have a DAO chain that has maybe things here, and maybe you have a ZK Snark chain that has a bunch of primitives for running zero-knowledge proofs. And you can pass it over to the mixnet, and you can actually customize stuff, and these contracts, not just you as an external user, these contracts can then move stuff around there and control that with their own logic on-chain. That, I think, opens a huge door to design, and by allowing not just native code, but smart contracts to do that on both sides, smart contracts that communicate on both sides, we allow a huge space for rapid development in this area, which I think is really the new frontier of blockchain interoperability. So we look forward to seeing that end of this year, early next year, and we are waiting for Cosmos Stargate to finish, and we are following their development with our IBC development. So I think this could be a really huge shift. So if you get in now on CosmWasm building your contracts that run on many chains, in half a year or so, you'll be able to have those contracts actually talk to multiple chains, one contract. So I'm switching gears now. Now that you're, so if you're a techie, this is where it's focusing tech heavy. If you just wondered what it is and how it's used for your project, well, we covered that. So digging into the tech here, how does CosmWasm work? We use wasmerlo to run the bytecode. It's a Rust project. It's pretty solid thing. A lot of other people running it, Nia Protocol, for example. And we precompile, it precompiles WebAssembly to sandboxed native code. It has different backends. We're using single pass, which is a very quick compiler, has no real attack surface, and it makes a bit slower code. It runs about 20 times slower than native Rust code. You could use an LLVM compiler. It takes that WASM, compiles a really, really optimized native code, and actually runs about half the speed of native Rust code. So your WASM can basically run more or less native code and full crypto on it. The problem with that one is it takes a while to compile, so the compiling step could be an attack surface. So we're looking at doing some, permissioned control of uploading it permissionless with single pass. And if you need the extra performance boost, we can have a permission step that has some people validate this okay before compiling it down to LLVM, because otherwise you can kind of slow down the blockchain considerably by running bad or malicious WASM that can just slow down the compiler a lot. But yeah, so it does that, as lots of different functionality here, and it runs native code that's completely sandboxed. There's no access to syscalls. It is metered with gas, injects gas metering involved in it, and all CPU usage is metered, and it's isolated memory space. It records its own memory, it has metered CPU usage, and it can touch nothing in the system. The only thing it can touch is imports. We provide some imports there, and we can then write defensive code to guarantee these imports are safe. That's our virtual machine layer, which wraps around Wasmer. So we have CosmWasm VM, which wraps around Wasmer, that provides our custom imports. we provide read and write access to a subset of blockchain space. We provide like a subkey under a prefix under the blockchain Merkle tree, and in that prefix it can read and write and nothing else. And we can limit how much it can read and write to that space. It can query other modules, read only in a very specific API to other native modules and contracts. And we can add more blockchain-specific APIs, which are also called precompiles. This will call out into the blockchain itself to do some stateless logic. Currently, we have address formatting because we support multiple chains. They're different native address formats. So we can't compile that in the blockchain. We have to say, well, convert a string address to a binary address is blockchain specific. So we call out to the blockchain itself to do that. We could add things like, signature verification, like Ethereum does, precompiles. Other stuff could go in there. And we can meter everything with gas. We allow no network access, no non-determinism, and no jailbreaking. We also disallow any float operations, which are theoretically non-deterministic. There's no random access here, obviously, because there's no syscalls, and we don't provide it. So we basically guarantee you cannot break consensus state. They will act deterministically. We don't allow multi-threaded. There are few WASM arguments. We go through all the WASM opcode, and if they use anything that's not in our safe set of WASM, we reject the contract on upload. Memory versus storage. So while we have this, we make the difference explicit. In Solidity, they mix them together. Instance variables and state storage are transparent to the user, which can be nice for development, but it's hard to reason about. In our model, the code has fast access to RAM, native speed. It has almost unlimited RAM. You can allocate currently, unless you set another limit yourself, you can allocate 4 gigabytes of RAM in your contract. You can explicitly set that less, 32 megabytes or 5 megabytes, but you can get up to that much. You can't actually use that much because CPU limits. You cannot write 4 billion zeros in space in a CPU gas limit, but you can allocate as much as you need. So any memory you can write to, it just will give you that memory access. So great, memory is cheap. CPU costs and writing storage and reading is very expensive. The price there is much, much higher. So we want to make that very explicit. You have to explicitly read and write to the database. So we have a simple interface that allows you to read and write typed data from the database. Great, but you have to explicitly do it. I think it's a critical difference from Solidity. Also, security first. We define security. So we looked over the list of, OpenZeppelin exposes the top 15, 20 security holes, exploits that are known in Ethereum. And we went through that and made sure that we could patch all we could. Reentrancy is impossible to design. We use an actor model. I'll get to soon. Overflows and underflows. Rust will panic if you do that. We said it that way. Unexpected ether is a bad design pattern. You can have trivial bugs because we can send tokens to the contract. Delegate call, we don't allow it. We have another way of doing those proxies of migrating code. Default visibilities, you have to explicitly set them. So we went through this whole list basically and closed all we could by design. In particular, we use the actor model for dispatching messages. This negates all possible reentrancy attacks. So rather than your contract A calling to contract B, and then contract B calling to contract A, and contract A is not persisted all their data in state, some in memory and some in database, and that gets all kinds of little subtle flaws in Ethereum, kind of like limit the gas this has, so it can't really call back into your contract. This is really bug prone. What we do simply is use the actor model. That means actor model, you get a message and you return messages. So your contract will process it and return the message. So if I want to call that, when I say basically I do my work, I save my work, and I return a message that we execute on other contract. That means I do not get a result from it, but it means I am done of saving my work before it starts. All you get to know about is whether it errored or not. We run all the messages you dispatch in the same transaction. If any of those contracts fail, then it will revert the entire transaction. All state changes get reverted. So I can basically say if an escrow happens, I will optimistically update the escrow got sent, I delete the escrow, and return a message to move the money. If that succeeds, great. If it fails, then it reverts the whole transaction and act like nothing ever happened. My delete escrow command is also deleted. That is usually the error handling you want. It's only one you have here. You can do complex logic to try to get other use cases there. It is kind of possible. Returning messages back is possible. It's not, it's a little trickier, and we'll demonstrate that, but basically the standard use case of just assume it works, and if it errors, roll back everything is the only one you get by default, unless you really try to do something else. There's no reentrancy possibility. And you don't forget to check the return value of a send. It might return a 0 or false if it didn't work. Don't worry about it. It just always checks that. Like you said, we have built-in overflow checks. We have explicit API for query and handle methods. So you have to explicitly add those methods that you want to be exposed. They don't just happen to be exposed. And yeah, everything's very explicit there. You have to call into stuff and make sure that there's no loops possible. And we use the Rust language. We ensure the Rust language has a lot of functionality to ensure contract safety. That means we take advantage of, they have a lot of control of type safety, of memory usage, of mutability issues, and so often you compile code and it yells at you 3 times the compiler, and you realize, hey, these are subtle bugs that I forgot to handle. I didn't handle this error case here. And so the compiler will give you warnings or errors on many, many possible cases, and by utilizing that, you can avoid large costs of bugs because the compiler checks your logic quite a bit, whereas our framework doesn't allow these larger design issues to happen. Rust also provides first-class test tooling. They have quick check, they have fuzzing. You can do very, very complex testing with Rust as unit tests on the Rust code before you compile to WASM, which allows you to get very, very high levels of reliability and security on your code. You don't have to upload code to a virtual machine and run it. You can actually run it as Rust, natively link stuff, and then when you've tested that heavily in unit tests, you then compile it and run high-level integration tests on it, seeing how it works in reality with a real thing, but you can get much lower ones, give you full stack trace exactly what failed, and it's really, really nice compared to trying to debug Solidity, for example. So yeah, contracts and native code is love. We are not trying to make a general purpose smart contracting platform. There are many other ones that are doing that very well. For example, Nia Protocol is just allowing you to write smart contracts on their platform. And they do an amazing job doing that. Also using WASM and also using wasmerlo background. However, it's just contracts. And for some people, that's amazing. Many other platforms, however, are currently building out native code. They are building a blockchain with custom native functionality that may need privileged access to various things. You might need privileged things you not want exposed to generic contracts, right? They control the value set with their staking algorithms. They want to have very optimized cryptography using native code. They want to have that native code. So we allow the integration between contracts and native code. And I think that's what really differentiates us from many other projects, which are awesome projects, but we are going for a different route. We are basically not generic smart contracting platform. We are one that ties deeply to native code. So you can currently call into the bank, which is coin transfers and staking modules in Cosmos SDK and other contracts, but you can easily extend that. So for example, on Terra, they wrote a swap, more of a trading swap DEX thing, and an Oracle modules for exchange rates in Go native code. And they wanted to add smart contracting capability on top of it. So we allow that. We worked with them to add extensibility. They can now expose an API, so and don't have to recompile a Rust code or anything. They expose it in their blockchain, the API they want to expose, and it's passed down into our contracts. A generic contract can run on their platform with no modifications, and a contract can import a crate to add their extra custom types, and it will then mark a feature flag that needs Terra. And that contract then has access to their swap and Oracle modules, certain queries and messages. And it can call into the native code very nicely, transparently, just as easy as it calls into the staking module. However, that module isn't flagged with a Terra flag, which means if you try to upload that Terra specific contract to another blockchain like Enigma, it will reject it because it requires the Oracle and swap contracts. So we allow you to flexibly do this. So you can have very generic contracts that rely on none of these extra pieces, which can run in any code. And you can have custom contracts that are really chain specific, that make use of all the native APIs of one chain and are only chain specific. But all that learnings you've had for tooling, for dev environment is the same setup you have. You just have a new API call extended for this chain. So we allow these contracts to run on one chain or multiple chains. And the more you customize it, it's great. But all that knowledge you have, all of that learning you have as developers can be ported to the other chain. So if you learn how to write Terra-specific contracts, that's wonderful. And now if you want to write contracts for another chain, just if you don't use the swap and Oracle modules, that contract works everywhere else. You can write your ERC20 modules, you can write NFTs, you can write your other stuff out there all you want, your DAOs, as long as you're not relying on those modules. The same tooling you've learned will work anywhere. So it's a really opt-in to native code. And now I hope you've enjoyed this. And I'd love you if you're interested in CosmWasm, if you think it's cool for your project, if you want to embed it into your blockchain, if you want to start developing on it, that's wonderful. You can learn more about us, CosmWasm.com. Also links to our documentation and gives you a little overview. And links to our Twitter account and our Medium account of various other things. Find us on Twitter. Please follow us there for latest news. On GitHub, you can find CosmWasm. CosmWasm is our main entry point, and we have a number of other repos as well. And on Vimeo, you can look for CosmWasm to find a list of our community calls. We have a bi-weekly community calls, which are recorded, and you can see what our updates. So we get a half hour to an hour discussion of our current updates and roadmaps, if you like to watch videos and follow our current progress. It's a very nice way of keeping an eye on it every 2 weeks. And finally, we will be involved at the hackathon. So we are working with Terra on the hackathon in the next few days. So please join that. I'll be doing a workshop on that one. And there's a lot of resources that Terra has also assembled on how to onboard. So come, please join that. Write your first contracts. Learn how to use the Terra DEX with smart contracts and write CosmWasm smart contracts in general. We've read a lot of stuff. So I'd be very happy to see you there and get your hands dirty as developers using it. If you are wanting to, you can also join our Telegram channel. We have Discord channels. It's all linked from our website. If you are a zone that is interested in building it, reach out to me. My name is Ethan at Confio.tech or Ethan at CosmWasm.com. You can reach out to me, and I'm also curious, after 1.0, we're curious about integrating with other blockchains besides the 5 or 6 we are currently working on. Thank you very much for your time. I hope you enjoyed this talk and look forward to seeing